Okay, for those of you listening at home, hi Jonah, hi Ella. We are going through the Chapter 8 Practice Test, version 1. And the answers are as follows. The first answer, actually the computer got wrong, which is not exactly inspiring confidence. But number 1, it should be y equals 2 times the natural log of x plus c. They put 2 times the natural log of negative x for some strange reason, which is totally wrong and would be imaginary. But number 2, y equals negative 2 sine of x plus c. Number 3, y equals the cube root of, and this is all of this is under the cube root, 3e to the x plus c. So the c is underneath the cube root. Number 4, y equals the inverse tangent of parentheses x plus c. Number 5, y equals the natural log of parentheses e to the x plus c. In case you were wondering if the ln and the e canceled each other, they would have had it not been for the plus c inside the parentheses. Yeah.
So for like number 4, when you said parentheses, x plus c is the x plus c both in parentheses?
Correct, yes. The inverse tangent of parentheses x plus c.
Okay.
Yeah, so the c is inside. And number 6, same sort of thing. Y equals inverse sine of parentheses x plus c. So the c is on the inside. And it repeats 1 through 6. Number 7, slope field. Y over x. It's a little hard to describe, but if you go to the upper left-hand corner, if you go downward diagonal, all of those are slopes of negative 1. The upward diagonal, all the slopes are positive 1. Along the x-axis, all the slopes are 0. Along the y-axis, all the slopes are non-existent. They blow up. So they can be vertical. Yeah, I'll just draw it. This is a pain in the neck to try and describe verbally. Somebody, that's an old dead marker, I think, but I'll try it. Yeah, we'll work it out. It kind of looks like this. Yeah. So these are all negative 1. These are all positive 1. Except for the very middle. That is. This actually, again, I suppose this is kind of like a toss-up. So this is kind of sort of what it looks like. For number 7. For number 8, you can just go on columns. There are 5 columns. The left-hand column should have a slope of 4, so a nice steep positive slope. Second column should all have slopes of 1, so a perfect diagonal going uphill. Third column should have slopes of 0. Fourth column should all have slopes of 1, going perfect diagonal up. And fifth should have slopes of 4. So every single one of them, every single one of them should look like this, 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 this. And they should be identical.
So do you want us to draw the slopes of 0?
Yes. Slopes of 0 I do. Even though it's a little hard to see into the backdrop of the line itself. And by the way, on these slope fields, it's really, really hard to tell the difference between like a slope of 4 and a slope of 5. There's really no realistic way to say, gee, I wonder if that's a slope of 6 or something. I don't know. It's something bigger than a 1. That's pretty much all we got. So we have to calculate the number and then just make our best sketch. Make sense? This is number 7 and number 8. there's my marker. I feel happy again. Well, I mean, I was happy before, but I'm super happy now. Number 9. Find a differential equation that could be represented with a given slope field. This is a little tricky. It's looking as if dy over dx equals 1 over y would work. There are a couple other candidates, but pretty much you have to have a y in the denominator. The reason being, if you would have the y in the numerator, then as y got bigger, the slopes would get bigger. But here, as y gets bigger, as you go up, the slopes get smaller. You could have 1 over y, 2 over y, 3 over y, etc. Number 10, this is a little hard. Dy over dx equals y minus x. Y minus x. Number 11, convert to polar coordinates. It is 2, 30 degrees. Number 12, convert to rectangular coordinates. 3 over 2, negative 3 radical 3 over 2. It repeats up to number 12. Number 13, it's a little on the exotic side. It's a big fraction. The top of the fraction is e to the x sine of x minus e to the x cosine of x all over 2 with a plus c outside the fraction. Any repeats on that? Number 14, the limit is infinity, positive infinity. And number 15, the limit is infinity. It repeats. All right? Let's before we start going through this, I promised Jonah I would do the correction problem number 5 on the worksheet, the one I goofed up the other day, on the video. So let me take a quick look there. The problem is this. As the limit as x approaches infinity, this is from homework 8E-1. Number 5, it's the limit as x approaches infinity. This is the one where I goofed up. I forgot to do the chain rule stuff. Of 4x sine of 1 over x. Now, first thing I'm going to do is pull the 4 out front. Because any calculus function you can pull the multiply constant in front. So it's going to be limit as x approaches infinity of 4 times, whoops, put the 4 in front, of x sine of 1 over x. Now, if you try plugging it in, it would be basically infinity. The sine of 1 over infinity is really the sine of 0. So the sine of 0 is 0, but infinity is infinity, so it's infinity times 0, which is, I have a flawless idea, and nor does anybody else. If we can get this to look like 0 over 0 as a fraction, or infinity over infinity, then we can use L'Hopital's rule, take the derivative at the top, derivative at the bottom. And as it turns out, you have to be kind of sneaky. I tried doing the cosecant on the bottom, and I think that might still work, but an easier way is this. 4 times the limit as x approaches infinity. In other words, making this into cosecant would be a sneaky way of putting it on the bottom. Making this, busting, sine of 1 over x over 1 over x is a sneaky way to get this in the basement. So multiplying by x is the same as dividing by the reciprocal. There you go. And if you notice, this is going to become 0 over 0. Sort of. So this is a candidate for L'Hopital's rule. Let's try it. Just be careful. Now forget the chain rule, as I did. If you've got 4 times the limit, whoops, as x approaches infinity, the derivative of sine of, I'm going to just write it up here, the sine of x to the negative 1 power. That's one derivative from this one. So the derivative of this thing is going to be cosine of x to the negative 1 times the chain rule stuff, negative 1x to the negative 2. I'm just going to write it like that for a second. So we now have negative 1x to the negative 2 times cosine of 1 over x over, and then the derivative of 1 over x is the derivative of this thing. It's negative 1 x to negative 2. You notice something happened? Yeah, the x's cancel, the negative 1's cancel, bam. So all we're left with, that's super duper nice. I wish I found that earlier. So it's now 4 times the limit as x approaches infinity of cosine of 1 over x. What's 1 over x as x gets huge? 0. What's the cosine of 0? It's 1, because the cosine is left, right? And at the 0 degree position, you're here. Oh, yeah. And then the cosine is 1, so it's basically 4 times 1. Better not misplay. I've officially redeemed myself, so you're welcome. And thank you. So let's try the practice test.
Okay, go for it.
Yeah, perfect. Questions?
Could you do number 10?
Number 10, definitely. I'll do it over on this side of the board. Limit as x approaches 0. Minus 1 over 5x cubed. All right. Now, if you plugged in 0 right now, what would you get?
I think our number 10 is different from your number 10.
What?
Yeah, I
Oh,
don't
this
know.
is
Oh, I'm
a
on 80
difference.
dash, whoops. I'm on the word whoops.
Yeah.
That kind of explains a lot. It was the flow field?
Yeah.
Got it. Okay. They'll actually take a little less time. That's even better. I'm just going to try to carry this thing over. Now, when you're doing slope fields, if they give you a slope field, they're pretty much going to mark dot, 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 dot. There are basically 25 possible places for slopes. One thing I watch for is easily recognizable slopes. Easily recognizable slopes I consider as being 0, undefined, 1, and negative 1. Everything else is kind of guesswork. It's like, is that slope of 2? Is that slope of 3? Slope of a half? Nobody really knows. So I see a slope of 1 here. I see a slope of 0 here. Sometimes I even mark them. This is a slope of negative 1. This is a slope of 0. What other ones? This is a slope of 1. The middle one is a slope of 0. This is a slope of negative 1. This is a slope of 0. That's something weird. This is a slope of 1. And this is 0. This is negative 1. This is blah, 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 yeah. All of these are... Do you notice that as you go further down, it seems to be getting flatter and flatter? I should actually write like that. It's kind of like a slope of 1, slope of 2, slope of 3, slope of 4, something like that. In other words, it's getting bigger. How much? I don't know. But this is getting steeper. This is getting negative steeper. This is getting negative steeper. That's kind of, oops, down here, I forgot these. This looks like negative 1. That might help. This looks like positive 1. That might help. This looks like something bigger. This looks like something smaller. All right, let's do a little detective work. Here's where x equals -2, x equals -1, x equals 0, x equals 1, x equals 2. Here's where y equals 2, y equals 1, y equals 0, y equals -1, and y equals -2. Now, they want dy over dx equals something. So, first question. Some of these things are only dependent on x. Like if x changes, they change, but if the y, it doesn't change. Like on number 9, it looks like x makes no difference whatsoever. You go all the way across on x, it doesn't make any difference to the slope. So that means that there is no x in the formula. Does that make sense? If you were, like, if the entire top row, if x made a difference, you'd see it change as x got bigger or smaller, but it doesn't. So it's got to be only something with y in it and nothing but y. In this one, does it look like it's only x or only y or both?
Both.
It looks like it's both. Because as you go across, it changes, and as you go up and down, it changes. That means there's an x and a y in there somewhere. So let's do a little detective work. I know that when x and y are both 0, this thing is apparently 0. Is there, I am noticing these. All of these are 0. The going upward diagonal. Is there any possible candidate that would do that? Like when x is 1 and y is 1, x is 2, y is 2, you get 0. What possible thing could do that? I know 2 possibilities.
Like an asymptote?
Well, kind of. In other words, you can make up your own formula using x and y. If x is 1 and y is 1, how do you get an answer of 0? I give you 2 1s. You minus them.
Yeah.
That's one possibility. So it could be either x minus y or y minus x. Does that make sense? So here, I look for the zeros because those are the easiest ones to start with. And it looks like 1 and 1 make 0, 2 and 2 make 0. That's looking like a good candidate for subtraction. So which of these is it? Well, it has to work for every single point. So let's take a look here. The 1s are nice, easy to find. When y is 1 and x is 0, I get 1. What do you think?
So it has to be y minus x.
Has to be y minus x. Why? No, how come? No pun intended.
Because that would be negative.
Yeah, if you'd have done x minus y, 0 minus 1 would have been -1. It would have gone downhill. Does this formula work for everything? Let's double check. Here, y minus x, what's 0 minus 1? That seems to match. What's -1 minus 1? -2. Does that look realistic? Yeah. Try here. What's, this is going to be horrible, sorry. But what is -1 minus -2? Positive 1. Does that look realistic? Yeah. And it looks like, how about here? What would you get? 0 minus -2? 2. 0 minus -1? 1. 0 minus 0? Does this look like it fits everything? We're good. It's kind of a detective problem, but look for the 0 slopes first. Those are usually, I mean, this does have kind of a cool, you notice that it's kind of a spirally thing. It kind of goes this way, and it kind of swoops up this way. It looks kind of neat, but that's, if you happen to graph the final solution, the y minus x, that, well, if you solved y by itself, you get a very exotic looking function. And those curves kind of represent it. Next.
Can you do 11?
11, yeah. Rectangular coordinates to polar? Yeah. Can anybody refresh my memory on the formula for polar coordinates? We usually use x, comma, y. What are polar coordinates? What, comma, what?
R, sine of it, or cosine.
R, comma, I mean, just in general.
Theta?
R, comma, theta. If you have, like, they're starting us off with rectangular coordinates, and what were you saying?
R cosine of it.
R cosine has to be of an angle,
Theta.
of theta, comma,
R sine of it.
R sine of theta is what will allow you to get what?
R, so that's what
That's x, comma, y. The reason is because, you remember, cosine of theta, comma, sine of theta is where you find a point on the unit circle? That's if you only have a radius of 1. If you have a radius of whatever you want, r, then this point is r cosine of theta, r sine of theta. And if you make the circle as big as you want, and you make the angle as big as you want, you can hit any point on Earth. Like, I could hit this point out here. It would have to have a radius of like 45, and have to have an angle of like 20 degrees, but you can hit it. Does that make sense? So this, if you memorize nothing else, memorize this. This is the key to transferring between rectangular and polar. Okay. So in number 11, they gave you radical 3, 1. Did they just give us r, comma, theta, or x, comma, y? Mm-hmm. Yeah, otherwise there'd be a degree mark or pi or something here. So x, comma, y is equal to this. So basically r cosine of theta is equal to radical 3, and r sine of theta is equal to 1. Any idea how to do this? Like, where would you start? I need some space. I hate erasing these slope fields because it puts so much energy into them. I don't know. Where do you start a problem like this? Like, if you just, ta-da, here's your test. What's something you could just brainstorm and try? Let's just say all they gave you was this. What's one thing you could try?
What do you do?
Sort of. If you had a formula you could plug it in. What's one thing you could do with the point? Just pretend you're in first year algebra. Is it 3, 5? What could you do with it? You can plug it in if you have an equation. We don't. Or you could graph it. Let's see where it is. Radical 3, 1. This is over radical 3, up 1. Does that look like that could give you anything? If you remember, this is a point on a circle. It's not a unit circle because it's bigger than a unit circle. I need to find two things. I need to find r. I need to find theta. Theta is here. R is here. Any ideas of how to find either one? Pythagorean theorem will find r. Drop the altitude, make a right triangle. This is radical 3. I should put that over here. And I have no idea what the height is. But the radius, actually I do know what that is. It's 1.
It's 1.
Yeah, that was stupid. And then the radius is unknown. So sum it up for me, Pythagorean
So
theorem.
it'd be r squared equals radical 3 squared plus 1 squared. So r squared equals 4.
Yeah, radical 3 squared is 3, 1 squared is 1. So r squared is 4, so it means r is equal to 2. Ever recognize that triangle, by the way?
So
It's a 30, 60, 90 triangle. By the way, that's insanely lucky. But, which angle is which?
Theta is 30.
Theta is 30. How do you know that?
Small angle.
Right. How do you know it's the smallest angle?
Function 1.
Right, it's just crossing the smallest side. So this must be 60. So we now know that theta is 30 degrees. And what was R? 2. So you can now 2, comma, 30 degrees. Is your polar coordinates. Okay. The main trick on these, graph them. Graph them. If graphing doesn't work, then use this formula. But graphing is usually a good idea to find out where you are, how big things are, etc. Okay. On this particular task, you will, this is not always going to be the case, but on this particular task, I can pretty much guarantee that theta is going to be a common angle. It's going to be a multiple of 30 or 45. In real life, that might be theta is 10 degrees, or 10.2859, blah, blah, blah. You'd have to do an inverse trig function to find it. So it could be at like, just for giggles, if I gave you this, 4, comma 3, and I want to get this into r comma theta. Graph it. Again, over 4, up 3. Does that look familiar to anybody, by the way?
Is that 45?
It's a 3, 4, 5 triangle, yeah. So the radius is 5, so you're half done. How do you find theta? That's not a common angle. Because 3, 4, 5 is,
We take, we really want the inverse of pi.
yeah, pick a trig function, as long as you have the two numbers that work.
We do like sine.
Sine. So sine of theta is equal to what?
3 over 5.
3 over 5. How do you get theta?
Inverse sine.
Take the inverse sine.
So theta equals inverse sine.
Inverse sine of 3 over 5, I have no idea what that is. But it's some sort of weird decimal, which, just for giggles, let's find it out. And my radians, let's do that in degrees just for friendliness sake. Inverse sine of 3 over 5. And I got roughly 36.8699 degrees. So what I would put on this thing is 5, comma, 36.8699. That's rough, this is approximately, but those are approximate coordinates in polar form. Okay. Next.
I have a question for that one.
Yeah.
How did you know the radius?
Oh, the radius. We skipped a step because the 3, 4, 5 triangle is a common triangle.
Okay.
But I would have done 3 squared plus 4 squared equals r squared. And it would have been 9 plus 16 equals r squared, 25 equals r squared, and then r is 5. Okay, sure. Thanks. Pretty much anything is fair game.
Maybe 12.
12. Okay. Convert polar to rectangular. So 3, comma 300. This is actually a little faster, believe it or not. But again, it's not a bad idea to draw it. 3, comma 300 degrees. How do you draw that in polar? What does that look like?
So you go 300 degrees from 0,
Okay.
and then go 3 spaces back.
Right. So you're going to move 3 spaces out. I would say it would probably be easy to draw the circle first. It's up to you. So here's the circle of radius 3, more or less. And then rotate around 300 degrees. This is 270, this is 300. So we're right here. Now I want to know x, comma 1. Any idea how?
Use that formula, right?
Use this one. R cosine of theta, R sine of theta. So this is going to be, go ahead and you tell me.
3 times
sine of 300. And these are common angles, so you should be able to give me the exact value of cosine and sine. What's the cosine here? We have two candidates. It's over a little to the right.
So
It's positive or negative cosine?
positive,
Positive, it's to the right. A lot or a little?
a little.
A little. What fraction is that? Two possibilities for fractions for 30 multiples of 30. And if you get stuck, you can always draw a 30, 60, 90 triangle. That'll tell you the two fractions.
So 1/2.
1/2. Yeah. The other one is what?
Radical period.
Radical period 2. Correct. So 3 times 1/2, this is 3, 1/2, comma, what's the sine of 300? Positive or negative?
Negative.
Negative, because it's down. A lot or a little? A lot. So what is it? 3 times what? Negative
3
radical period 2. So your final answer is 3/2, comma, negative 3 radical 3 over 2. Does that make sense? Next.
13.
Yeah, I was expecting 13. 13, I actually wrote it backwards. It's supposed to be e to the x sine of x. Let's erase this one over here. This looks like a product. Now, let's go back to the very beginning of integrals. If you have a, what's the product rule for integrals?
Substitution.
Right, there is no product rule for integrals, it's substitution. Now, in this particular case, we have two radically different species of function being multiplied together. If you did a u equals x, well, u equals x just transforms it into e to the u sine of u du, which doesn't help. It's just a different letter. If you tried u equals sine of x, you'd be hoping for cosine of x for your du. I don't see that. If you're looking for e to the x, what's the derivative of e to the x? What's du for that? What's the derivative of e to the x? Another e to the x, and I don't see that lying around either. Looks like substitution will not work. There's one other tool in our tool belt. If you have a product of two dissimilar functions, what do you use? There's only one other formula I've ever given you where it has a product of two things for an integral. Jog your memory. Oops. This go away. Yeah, integration by parts. What is that? UV minus dV. Correct. The integral of udv equals UV minus the integral of dV. Integration by parts. This looks like a good candidate. Can anybody suggest a candidate for U and a candidate for dV? There's some argument for doing either or. Do you remember, now, do you notice both of them? The rule is pick something that has an easy derivative that gets no harder, and pick something that has an integral that gets no harder. You can kind of do either or here. Do you notice that e to the x, what's the derivative of e to the x? E to the x, that's nice and easy derivative. What's the derivative of sine? Cosine, that's almost as easy. So you can kind of take a pick here. Whichever one you think is easier. U sine of x, okay. And by the way,
Doesn't matter.
every once in a while, at first glance, it doesn't seem to matter because both of them seem easy. Just want to prepare you in case you go like 4 steps in and it just conks. Like, when will you recognize a conk? When you write this out and you get another integral, you're hoping this integral is easy. If it's horrible, you know, oops, didn't work. Then you just do the other way around. That does not mean you did anything horrible, or that you're bad at this or anything. People with 8 PhDs in math when they're doing integration by parts, unless they've just done this particular problem 20,000 times, they'll have to guess. It's like, and it's just a normal, again, PhDs in math go 4 steps in and say, oops, that was the wrong way. Try the other way. It's normal procedure for that. That's why I don't have a huge number of problems on that test. So, sin of x, and this is e to the x, dx. What's d? Cosine of x, dx. And then what's v? E to the x. Okay. Let's see what happens here. The integral of u dv is u v minus the integral of v du. Try it. Let's see what happens. If it doesn't work, we can try the other way around. So which u?
Sin of x.
Yep. And then v?
E to the x.
E to the x. Okay. And then v?
E to the x.
And then du?
Cosine of x. Oh, it's just the same.
Yeah, it looks like we have the same issue. Now that's not necessarily fatal. Try it again. There are some problems where you have to do the integration by parts again. Now, my instincts would be just like yours. I look at that and say, uh-oh. Like, that looks like exactly the same difficulty level with the first one. It looks like we didn't make any progress, we just moved it sideways. Try it again. Just do this one. What is, now I hope you don't confuse this U and this U. Should I do U2? That's where the discussion of the group came from. Okay. Why not? U2 and dV2. What would you use? It's perfectly okay if you do the same sort of thing. I would actually recommend you be consistent. So how about U? Cosine of x. And then dV? E to the x, dx. Go for it. What's du2? Negative sin of x, so dx. And then what's v2? E to the x. Good. Let's rewrite this. So it's the original function is the integral of e to the x sin of x dx is equal to this thing. So it's okay if I just arrange this as e to the x. I just put the e to the x first. Minus, let's do the integration by parts. It's going to be u to v2 minus the integral of v du both 2. So do u2 v2, or uv basically. Yep, times. Yep. Cosine of x times e to the x. Okay. Minus the integral of, yeah, e to the x times negative sin of x dx. Does this simplify at all? Yeah, pull out the negative. So let's rewrite it from beginning to end. Again, normally we don't even bother writing the original part of the problem. This one I suggest you do. Equals e to the x sin of x minus, I'm going to write this as e to the x cosine of x, e to the x cosine of x plus the integral of e to the x sin of x dx. Oh, whoops. I distributed negative. So this is going to become plus, this has become minus. You see what I did? I forgot to distribute this negative. Now what? See anything suspicious?
Yeah.
Yeah, so,
It's the
This
same.
integral is identical to this integral. Switch on the algebra part of your brain. What can you do?
Add.
You can add the integral to both sides. Sin of x dx plus the integral of e to the x sin of x dx. What do you get?
2.
2 integral of blah, blah, blah equals e to the x sin of x plus e to the x cosine of x. And technically there's a plus c when you're done. But,
Divided by 2.
yeah, this is the integral we wanted. It's kind of like cheating, but it felt like we never actually evaluated it. Boom. This is called the cyclic integration by parts. It would go forever if you kept doing integration by parts, but just add it to the other side and we can just stop. Yeah.
Alright, instead x to e to the x sin x minus e to the x cosine x, because when you distribute
Yeah.
the,
Oh.
when you give, like, when you distribute the,
Oh, yeah. Oops. Hang on a second. Yeah, oops. My bad. Sorry. And then yes, so minus. Thank you. See if I'm making it again. And looks good. Questions? Looks good now. When will this cyclic integration by parts happen? Because sometimes you only have to do integration by parts once. Sometimes you do integration by parts twice and you actually get the integral. But what about now? How do you know it's just going to orbit forever and use this addition trick? If you keep taking the derivative of e to the x, will you ever kill it? No. If you keep taking the derivative of sine of x, will you ever kill it? No. It just repeats cycles of 4. This is just a cycle of 1, and this is a cycle of 4. If both of them just cycle forever, you're looking at a cyclic integration by parts problem. Okay. If one of them is cyclic and one of them is not, then one of them will eventually die and you can do it normal integration by parts. But if both of them just cycle forever, be prepared to do this trick. Okay. Next. How'd you do on page 1?
fine, after we asked you for help.
1 through 6? How'd you do on number 4 and number 6? Was it okay?
Yeah.
Okay. You had to get y by itself, that's why you have those inverse functions. Inverse tangent, inverse sine, for number 4 and number 6.
Well,
You wanna see it?
I guess,
Might as well.
Okay. Pick one.
4.
Number 4. Do f of the x equals 1? This is number 4. Equals 1 over secant squared of y. How do you solve this thing? What do you do first?
Get the x on the other side.
Yeah, get the x's on one side, the y's on the other. So,
Cross multiply.
yeah, cross multiply over. So what is this going to give you?
Dx.
Dx equals,
dy. Secant.
yeah,
squared
so
of y.
secant square root of y dy. Now what? How do you get rid of the dx's and dy?
antiderivative.
Antiderivative, correct. Take the integral. What do you get?
X equals tangent of y.
Mm-hmm. Plus c. Now, you do need to get y by itself. That's the catch. Do so. What do you get rid of first? Subtract the c. So if x minus c equals the inverse or the tangent of y. How do you get y by itself? Inverse tangent. As long as you do it to both sides. Be careful, do it to the entire left side. Inverse tangent. Inverse tangent. What happens here? Cancel. So y equals what? Yeah, of x minus c. Do you notice on the answer key, I did the inverse tangent of x plus c? And I did what?
Doesn't,
It's actually kind of a dumb reason. What is c?
you know,
Yeah, an arbitrary constant. What's 2 times c? Yeah, c. What's c plus c2 plus c3 plus c4? Yeah, and what's negative c? C. So in other words, c might have been negative in the first place. C is like infinitely stretchable. That's why they put the plus c there.
okay.
You could put minus c, I would still accept it. That'd be totally fine. Everybody good with that? Excuse me. Anything else in the whole worksheet? Practice test.
To do 14.
14, yeah. Evaluate each limit. There are 2 ways to do number 14. Whenever you have limits going to infinity, we actually ran into that at pre-calc, although we didn't call it a limit. What are you doing graphically when x goes to negative infinity? Like if you just look at the graph, where are you going? That's y goes to negative infinity.
Oh,
To the left forever. So if you're going to the left forever, you're watching what the graph is doing. That's actually hunting for horizontal asymptotes. That's what we use that for in pre-calc. Or we used that for in pre-calc, theoretically. So as x goes to infinity, one way or the other, you want to see if the graph flattens out. In this case, same sort of thing. What are the only terms you have to pay attention to? The dominant terms. So this is the pre-calc way to do it. The limit, as x approaches negative infinity, which means you're going to the left forever. I'm going to do that negative on top, negative x cubed over x squared plus 2. What are the only terms you really have to pay attention to?
negative x cubed over x squared.
Exactly. Does that reduce?
So negative x.
To negative x. So the limit, as x approaches negative infinity of negative x, take a guess. It's infinity, positive infinity.
Okay.
That's the pre-calc way to do it. The calculus way to do it is to do L'Hopital's rule. It's infinity over infinity, so you can just take the derivative of the top and bottom again and again and again until you get something useful. And you should get negative x eventually over some number. Over 2, I think.
In 14 and 15,
Ah.
be a fraction on the test side.
Oh, could it possibly be a fraction? Yes. That's pretty much if, and by the way, it'll either be obvious, like, I'll give you an example of one, a pre-calc version. The limit as x approaches infinity of 3x squared plus 7 over 2x squared minus 19. What would that answer be?
3s.
What's that?
3s.
Yeah, how do you get that?
You ignore the 7 and the 19.
Right. By the
That's
way,
infinity.
the permission to ignore these comes from x being huge. If x is going anywhere other than infinity, you can't do this trick. But if x is getting enormous, this is going to be huge number squared, piddly little numbers that got locked down into dust. So this would be 3x squared over 2x squared plus 3 halves. Okay. Now, if you did L'Hopital's rule, take the derivative of the top, 6x over 4x. Take the derivative again, which reduces the derivative. And that works just as well. Okay.
One, like, where it's not already put in a fraction, to do L'Hopital's or whatever, that, like infinity over infinity or 0 over 0.
Correct.
And they were like, I think some problems on the worksheet where we had to like turn something into a
Oh,
fraction.
yes, yes, yes.
It would give me like one like that on the test.
Will there be one like that on the test? Maybe.
Okay.
If, basically if it's not a fraction, and you can't plug it in normally, if there's no obvious way to do it, then you be clever and make it a fraction. Like on the problem number 5 that I messed up, because I forgot the general. So you can make, I think it was like 4x, sine of 1 over x. Can you make that a fraction? Yeah, there are 2 different ways you could do it. You could do 4x over cosecant of 1 over x, which actually would have worked if I had remembered the table and stuff. Or you could do sine of 1 over x over 1 over x. Check and see which one gives you infinity over infinity or 0 over 0. I think that might have been part of the problem with this thing. This is as x went to infinity, I think. Yeah. So here, the top's going to infinity. Cosecant sine of, this is infinity over 0. So that's, yeah, that's one of the reasons why this didn't work. But this actually becomes 0 over 0, which is infinite. So it's possible. I'm trying to think of how hard it would be. We got 8th graders super duper early.
Yeah.
Well, I could go over those for a while. Any other questions? All right. We did the conversion back and forth. We did the slope fields. All right. And it's meant to be, this is going to sound funny, but it's meant to be a shorter test than usual. That doesn't mean you won't necessarily need the whole hour. Number 13 is a little bit of a time hog. The other one should be a little faster. Any other questions? Otherwise, the game plan is I will give you another practice test tomorrow. We'll be taking that in class. I'll actually include some extra credit problems so you know what kind of extra credit I'll have to throw in the class. We'll go over that on Thursday, and then the real test is Friday, and off. As a consequence, you have a week off of homework. Don't get used to it. Well, of course, at this point of the year, I'm not sure how much homework I'm going to give you. As after this, holy mackerel, how many weeks do you have left?
Like, well, I'm doing this one 3.
So this, yeah, so
Well, 3, well.
11, 12, 13, 14 is this week.
Not including the.
Yeah, not
Six
including
and
the
action.
exams, I guess.
Yeah, so 2 more regular weeks, and then final exams. Wow. So yeah, the homework is actually going to be kind of minimal, because we're going to start drilling for the final exam the week before. All right. Well, Jiminy Christmas. We did throw up anybody's schedule. I wonder if there's a class in there.
Well, they're always in.
But we go to,
You can just sneak over in there.
Yeah.
I think we can just call this early. So I'll let you go over there a little bit early. For those of you listening at home, God bless you all. Heal up quickly. We're praying for you. Bye.